All right. Welcome back, folks. We're going to continue and finish up the lecture that I started last time on transforms. And we're going to talk about perspective transforms to finish up, particularly talking about how transform representations can be used to implement things like linear perspective effects. But the main part of the lecture for today is going to be about texturing, okay, about texture mapping. So I'll wrap this up and then we'll come to that. Okay, perspective. So last time, as a reminder, we talked about how we can represent transforms, such as modeling and viewing transforms, such as scales, rotates, transforms, things like that, as well as like viewing transforms, like, hey, I have a camera in the world relative to these other objects that I've described in 3D, and I want to be able to see those other objects from the perspective of the camera, that kind of viewing transform. So we talked about all that last time. And then I finished up by saying, hey, are we kind of done here? And one really big area that's very foundational in graphics is that we're not done with is talking about perspective. Okay, so what's in perspective? Okay, so this picture here, you all know what it is. You're on a road, okay? Obviously, the white lines are parallel here, right? They're always the same distance going off into infinity if you measured it with like a tape measure. But it looks in this picture, of course, like those lines are converging to a point. And we understand that pretty well these days. Many of you have probably heard of linear perspective or even seen it in like an art class, maybe. And we know that parallel lines converge, or typically there are sets of parallel lines in a picture that converge. But of course, this was not very well known, in art, even though it's so central to drawing pictures that have a sense of three-dimensional realism. If you try to draw things that are representational or to illustrate things that are representational, it's really core for that. This wasn't really well known. So in the 1200s, artists are trying to make things look very realistic. In this piece of work, on like a wooden panel, a painting on a wooden panel, there's a lot of realism in this picture, in the depiction of the characters, the scenes, animals, other things. But we would not call this sort of persuasive from a three-dimensional sort of an appearance, okay? Later, we're sort of getting a bit closer. So this is by Giotto towards the end of the 13th century. And you can see there's sort of more elements of this three-dimensionality. There's a sense of this being like this central building here, or this the central building with these columns and this covered area, having sort of an internal cavity to it that's visible, or similarly up here on this balcony or this balcony here, or this tower having a sense of form to it, a volumetric form to it. But it doesn't look quite right. I think you can probably see that visually. And one of the things that we can look at is, there's sets of parallel lines here. For example, this set of parallel lines here between these two that converge over here. These parallel lines here actually converge at a different point. These parallel lines over here converge this location. If you think about reasoning about this architecture, we'd actually expect that all of these three pairs of parallel lines actually would all be parallel to each other in 3D. And if you know about linear perspective for an art class, you'd actually expect all of those to converge to a common point, like a common vanishing point. Other examples of parallel lines like this one and this one have wildly different centers of projection compared to these other locations. Okay, so this is one of the aspects of what's not quite going right here. And it wasn't until the 15th century, the 1400s, that this was really worked out, okay? Worked out in detail. Brunelleschi has this really famous example of working this out. And the way that it's constructed is almost like a science experiment, okay? Brunelleschi says, hey, if I stand in the world, this is in Florence, say, if I recall this correctly, at the doors of the Florence Cathedral and look across this small piazza towards, or this plaza towards the baptistry, which is the building that you can see there in green and white marble, then sort of the experiment is, hey, can I draw a picture so that when I hold it up and look at that baptistry, that building, like the picture is, all the lines are in exactly the same place as reality. Okay, this would be kind of a good test of whether we've mastered, the mathematics, have the right kind of a geometrical theory in order to be able to reproduce this apparent visual appearance. And he does that. You can see what's happening here. He has actually the picture of the baptistry on a painting that he's holding in front of his face, pointing away from his face. Why is he doing that? You can see there's a little hole here to which you can put up your eye. So this concentrates your sight line, as you can see annotated here very carefully. And here's a mirror that has another hole in it. So by looking through this hole and looking through that sight line, you can put it into a very specific point, in this case, on a specific point on the door of the baptistry. And of course, the mirror will reflect the rest of this painting. So you can see the painting reflected here, and you can see a part outline of the baptistry behind it. Of course, you can move the mirror away back and forth as well to compare the two. Okay, so they're sort of going for geometric perfection between reality of the appearance of that architecture and all its parallel lines compared to a drawing. Okay. This really had a profound effect in art, okay, in the realism of representational art. So one example is by Ghiberti. He worked in Florence as well, early in the on these two doors. I think these are on the baptistry as well, actually. The north door and the east door separated by like 20, 30 years in his career. At the beginning, they hadn't really worked out all linear perspective completely yet. And then by the time he did the east, that's when he did the north door. By the time he did the east door, they had, and you can kind of get a sense on the left-hand side, there's these scenes that are almost more like those early Renaissance paintings I showed you earlier. There's a lot of realism, but it's more like of like a little scene, a little diorama. Whereas on the other side, on the east door, there's a great sense of depth. There's trees in the long background. There's architectural buildings with columns that create a sense of, like the columns getting smaller as they recede away in depth. All these kinds of things that happen visually in the real world for us viewing the world, and that are represented in linear perspective. You can see also in this example how these arches are sort of, following this converging set of lines. This is used in things like this picture. I mean, like it's just a great sense of depth. It looks very realistic, almost like you're standing there. Because there's extremely famous paintings that, leverage this. Leonardo's famous Last Supper uses actually compositionally. So the converging lines, if you sort of look here on both the ceiling as well as these columns on the left and right, converge on the head of Christ in this painting of the Last Supper. Okay, things like that. Okay. Sort of a whirlwind tour of some things that happen in art history as they relate to some of the things we're going to talk about today. Now, one of the, that's a good question here. If they didn't really know about perspective at the time, how could they make architectural designs to make the buildings? I really like this question. And so one of the things about it is that you don't need to draw in perspective in order to create, for example, like plans for a building. In fact, I talked about this last time when I described, let me just go back before this slide here. I talked about being able to project, for example, like a three-dimensional model onto like a plane in X, Y, and Z to create what we call plan views, like sections, elevations, these kinds of things as engineering drawings. These are actually really helpful already, in many respects more helpful, so like blueprints. These are like kind of blueprints you'd have for like a construction site. And being able to draw it in perspective was, at least, don't get me wrong, it's helpful in engineering too. But at this phase, it was actually more for being able to create a rendering that looked like you would see it in the real world. It visually appeared like you would see it in the real world. To understand how to do that, all that linear perspective stuff actually used something called the pinhole camera model, right, as the geometric sort of anchoring. So, oh, yeah, good question. Is the mic buggy for anybody else? Seems okay for a lot of people. Okay, give me a, put your hand up or something if things are getting quirky for you, so I can debug on my side. Pinhole camera model. Pinhole camera model is very simple idea, but extremely powerful. We're going to use it many times in this course. For example, when we talk about ray tracing, we're going to use it right now when we develop linear perspective transforms for use in rasterization type graphics. So the pinhole camera model, right, says that if you got like a camera on one side of an imaging system that's composed of a pinhole and then a light projection area, like call it a film or a sensor plane, then you can figure out where the light from specific points on the real object, the real candle, are going to appear by tracing rays, straight lines, through the pinhole from the point on the real object and then see where they would converge on the image plane. Okay. Simple idea. And you can build, of course, cameras that actually work under this principle. You can just make a hole in a piece of paper and actually make images inside a dark box that look this way. If any of you have taken Professor Alyosha Efros's and Angju Kanazawa's computational photography class, 194-26, I think, or the mezzanine class 294 of dash 126 or whatever it is. Anyway, they have you build a pinhole camera under these kinds of principles. Okay. And let me see. Okay, so we're going to use this model and just, do the geometry on it in order to derive what the matrix, when I say transform here, I'm now starting to think of it in the terms we developed last lecture in terms of the matrix that can be used in order to project three-dimensional worlds onto image planes such that they look like, this linear perspective drawings that were made in the Renaissance and that were happening because of a pinhole camera type imaging assumption. So let's go ahead and do that. Okay, so we'll derive the projective transform just by this setup, which is a redrawing of the last one, but just in sort of flatland this time. Okay, I just drawn it sort of as a section. That is, this is point X, Y, Z, but Z is coming out of the screen here. And let's say we had the pinhole at a point C over here, okay, for center of projection. And we have an image plane over here at a distance D away from the point C. Okay, does that make sense? Oh, sorry, I totally misstated that. Z is to the right here. And where did I have this? Oh, I guess Y, you can think of it as up and X out of the screen. Anyway, the key is that Z is left to right here. Okay, so what is the distance at this point from the center of projection? It is Z. Okay, because this is Z, the center of projection we'll assume is at the origin, so the distance away here linearly is Z. Okay, so we can go ahead and we want to figure out where this scene point from an arbitrary point XY is going to project at depth Z onto the image plane. But we can do one thing here, as you saw in this pinhole camera. We all think have a good sense of this. You heard this before. Images that appear inside a pinhole camera, or any camera in general, are flipped upside down. You can see the tracing of the rays here, Y. We know this is happening inside our own eyes, right? Our own eyes are well approximated by a pinhole camera model. And so on our retinas, we have optical images of the world that are also inverted like this. Instead of doing that in graphics, which we could totally do, it would present no problem. But instead of doing that, we can actually just do a trick here. We can actually put the image plane in front of the center of projection. You see what I did there? Instead of over here, I can just say it's going to be here. And we can pretend to project the light onto this plane instead of that one. So we just sort of pre-flip it and the image is going to appear right side up instead of upside down. This is really common in graphics rather than doing it the other way and then incorporating the inversion again. Okay. All right. So now in this case, what we're trying to do is to figure out the key thing, which is if I have a point XYZ in the world and I project it under a pinhole camera model onto an image plane that is at a distance D away from the center of projection, how large is that point, or how tall is that, the displacement of that point going to be? Okay, as you can see, it's smaller over here than it is in the real world because of convergence, right? So we want to know this thing for a general point XYZ, where is it going to project to? And in particular, we'll want to know what this height is here. Okay, and it's really simple. It's quite amazing. Okay, people worked on this for hundreds of years to try to understand it, but actually the math is almost trivial once I set it up this way. It's just similar triangles. Okay, it's just similar triangles. So the X displacement here versus Z, right, is the same is similar to this triangle here with the unknown quantity over this distance here, which is D. Okay, and yeah, good question. What does the center of projection mean in the real world? Which point does it correspond to? Think of it as the location in the world where we're going to position our virtual camera to view the world. Okay. You set up a 3D world, but you actually have to look at it from a particular location. You can think of it as an eyeball. You can think of it as sort of the hole in the lens of a real camera that you went out into the world from. Okay. Think of it that way. We'll get into some other optical effects about real cameras and lenses, particular depth of field, things like that, and depth of focus, things like that. later in the course, so you can omit that now. But for an sort of intuition relative to your eye, you can think of it as going into the world and positioning the pupil of your eye at this point C in the world, okay? And then looking in a particular direction. That has to do with the look at transform that we looked at, or that we derived last time, okay? Okay, yeah. I'll connect a couple of these dots explicitly again in the sort of overview recap at the end that connects how those viewing transforms to camera space last time connect with this projective transform. But for now, sort of think of it as we've looked in the world before from a camera at a particular viewpoint, looking in a particular direction at a 3D world, use the mapping that I showed last time to put it into standard camera space where the z-axis is pointing backwards, okay? And then now we're trying to figure out, okay, I got that world in regular camera space, but it doesn't have any linear perspective yet. We're going to project all the triangles in that 3D world onto this image plane. And for every triangle that has a corner, for example, at the location XYZ, where is it going to project to in XY on this image plane D? And the answer is given by this similar triangles formula where the displacement, this distance here is given by this equation. Okay, and you can convince yourself very quickly, it's just going to be by similar triangles, it's going to be x times d over z. Okay, so we map from x to x times d over z, y to y times d over z, and z is going to project to d. Okay, in at least this picture that we look at here. I'm going to revisit that. That won't be exactly the way the transform works. That's most commonly used for reasons I'll explain later. But from this picture, for projection similar to like a pinhole camera, this would be the exact mathematics. Okay, so how exactly we're going to represent this simple math, but how do we represent it with the matrices that we looked at last time? I sort of promised that we'd be able to represent all of the modeling and viewing stuff that we had last time, as well as perspective transforms using the 4x4 matrix, homogeneous coordinates matrices that I described last time. And the key to look at here is to recognize that the trickiness about it is that we have to divide by z because of this similar triangle foreshortening effect. And to form it as a matrix, we're going to use the homogeneous coordinates and the definition of that from last time, but we're going to extend it, okay? So let me show you how it's dealt with in the general case for 3D graphics of this kind, which is the way that these kind of transforms are represented in things like OpenGL, Direct3D, or other real-time graphics types of systems. So in general, what we do is we have a point P and a point in the world XYZ. It can be represented by any homogeneous coordinate, 4-element coordinate that has this form, WX times WY times WZ with W in the last position. Now, all of these points of this form, we're going to say are all equivalent to a point in the world at position XYZ. Okay, this is different than we've seen in the past. In fact, this is the first time that we've seen a non-zero or one coordinate or considered that at this location, okay, and viewed that to be acceptable. And in terms of the kind of matrices we're going to look at, it's also going to be the first time we're going to have a non-zero term in the last row here. Up to this point in all the matrices that we've looked at, if you go back and take a look at them, where you noticed it before, we've never had a non-zero term there. And in particular, what we want is to have the output of this projective transform, Q, be equal to some matrix. This would be the projective transform matrix, operating on an input point XYZ1 and getting it to come out. If we could do this, my claim is that, okay, we're going to have satisfied what we're trying to accomplish on the projection we're trying to accomplish on the previous slide. We can want to come out as XYZ over, with the last coordinate Z over D. Okay, if we did that, and this matrix would accomplish it, can you see that? XYZ is left the same, but by just having 1 over D here, in this coordinate, it's not diagonal, this matrix, right? It's in this column over here. Then the output homogeneous coordinate is going to be Z over D. Then we'll be done. And the reason we'll be done is that this point here, according to this definition of homogeneous coordinates, to figure out what real point in the world it is, we need to normalize by D over Z to get this to go to 1. Multiplying by D over Z takes us to X times D over Z, Y times D over Z exactly as we wanted, and it takes Z over to D, okay? So, so not much happened there. Not much happened there, actually. Okay. We just extend the definition of homogeneous coordinates and under this notation, and then we use basically something non-zero in the bottom row here in order to leverage, the common representation, this 4x4 matrix representation from last time to get us to do what we want. M. What is M used for? Again, M is just a general transform that we used that notation last time. It takes something, some point in, some 3D point in, and gives you some point 3D out. Could be a rotation transform, translation transform, looking transform, all those things. In this case, the M in particular is a perspective projection transform. Okay. Okay. And so one way to think about it is that last time we had a way to model the world and view the world. That's often stuck together sometimes when we want to refer to it as sort of the model view part of a pipeline of transforms that we're going to consider. Things like a dinosaur in object coordinates relative to its own center, of coordinate system, like around its own center, modeled beautifully there, then modeled into the 3D world, maybe instanced in multiple 3D locations with multiple transforms, and then a camera viewing those from a particular perspective. So that kind of viewing transform last time. And then finally considering, okay, what's the kind of perspective view on that scene that will tell us the parameters, in particular this distance d in this pinhole model, to project that set of three-dimensional meshes of the dinosaurs onto an image plane with perspective, okay? And believe it or not, that's it, okay? So I'll give you this very abbreviated art history lesson. This mathematical model we just looked at produces all linear perspective effects correctly. Converging lines, vanishing points, things like the fact that closer objects to the camera will appear larger in the image than objects of the same size that are further away, and in the right kind of proportion, okay, of decrease in size with distance. All of these things will just come up perfectly, it turns out. And it'll be very much like the way it visually appears to us in the world, very familiar visually, because our eyes operate, under a pinhole camera model. But one thing I left off here is, how do you actually specify the perspectives? Okay, because I said, okay, there's this D parameter that I mentioned here. So I swept a couple of how do you get these parameters? I swept them under the rug, and I want to talk about that a little bit now. Okay. Sort of how do we set the specific parameters in that projection matrix? The key idea that I want to talk to you about now is actually going to flip us from math back to thinking like an artist. In this case, thinking like a photographer artist. Okay. And I just want to show you a sequence of pictures and make some observations about that for you relative to photography. So what you see here is a sequence of photographs, okay, that have little annotations in the top left of a distance, 16 millimeter, 24 millimeter, 50 millimeter, 135 millimeter, and then 200 millimeter. So increasing kind of clockwise this way, okay. That millimeter number refers to the focal length of the lens, which for the purpose of today, you can think of as like the D, okay, in that image. D, okay, was the separation between the pinhole and the image plane. Okay, so 16 millimeter means a short distance in the separation there, and it increases up to 200 millimeter, which is a lot more, right? It's more than 10 times the distance between the image plane and the pinhole. Okay, now, but this is in a real camera with a real sensor, and the way you affect that is typically by either using a zoom lens, which changes this focal length continuously, or you might sort of swap out lenses with different focal lengths. And what you can see, the next thing I want to talk about is that's what these pictures are. Let's take a look now at the pictures themselves and make some visual observations. Okay, look at this one. First thing to notice is, okay, obviously there's a prime subject. It's this person standing here. The thing I want you to observe is that the size of the face in all of these pictures is the same in terms of pixel area. Okay, like the fraction of the area of this whole picture, the face is the same in all these pictures. Can you see that? This is not an accident. The photographer is deliberately doing something in order to make that happen. Okay, and actually, as we'll see, they have to do something very dramatic with their body in order to make this happen, the photographer's body to make this happen, okay? So notice it's all the same. And the reason that the photographer has done this is that these pictures are all portraits of this person, okay? The picture, if you say, what's this picture of? It's like, oh, it's a picture of, whoever this person is, standing in, in this environment, I guess, in this city. But the perspective is dramatically different, right, in all these pictures. So let's observe what's going on and just describe it explicitly. In the 16 millimeter, very short focal length picture, you see a lot of the city in the background, right? You see these buildings over here, buildings way over there. You see a lot of this, it almost looks like some kind of walkway here. Okay, a lot of that going on. There's a lot of the ground over here. And I want you to observe that as we increase the focal length to 24, 50, 135, 200 millimeter, we're seeing less and less of the city. You see that? Okay, we have part of these buildings, but part has been clipped off. Here we see even less of this building here. Here we see only like one of this, like just this window right over here of that building. In this picture, we actually don't even see the front side of that building at all. You notice that? So in this shot over here, it's like all we see is like the side of that building going down the boulevard. It is related to things like what the so-called dolly zoom and the vertigo effect, which I'll talk about in the camera lectures. Okay, now what's going on here? Okay, let's just take a step back and go to a bird's eye view and reason about what must be happening. Okay, what's happening here is that for the same sensor size inside the camera, when you have a very short focal length, it turns out you get a very wide field of view. We'll go into the mathematics of that field of view in the camera lecture, but for now, take my word for it, okay? A shorter focal length means you're gonna see like a wider field of view here, okay? The angle here is gonna be very wide. And in order to get the person's head to be of a certain fraction of the horizontal width, the camera has to be very close, relatively speaking, to the person. You see that? So that this really wide angular field of view of what you're seeing in the picture, the size of this person's head is going to be the width of the person's head relative to this distance here. Okay, so you have to be very close. Now, in contrast, if we went to the other picture, there was the longest focal length, that was 200 millimeter, okay? The angular field of view, it turns out, is much narrower. It's 12 degrees, if you want to know, for a full frame style camera, okay? So in order to get the person's head to be the same fraction of the horizontal width of the picture, as you can see, the leftmost and rightmost sort of, possible views from this telephoto lens, the photographer had to do what? The photographer had to, step back, walk back many, many, many paces, stand over here and take the same picture, or point back at the person and take another picture. You see that? So this is a very dramatic effect that the person is doing compositionally, and you get a totally different view of this scene. This is a very classic portrait view. It's more sort of cutting out more of the background and concentrating sort of like the visual interest into the person in this case, which is why it's called sort of a classic portrait composition relative to this view, which is fine as well, but this is a bit more of an environmental portrait composition. How is the angle calculated from the lens? Like, good question. Hold that thought. I want to go into it in this lecture because I don't have the right slides to support that, but we're going to get into that in full detail later in the course. But for today, what I want to observe is that I want you to think about the angle of the field of view. Okay, so in this case, 110 degrees, that's this angle here. And in this case, 12 degrees. And just recognize that in order to frame any particular picture of the scene, right, I was talking about like, where does the camera go? What is this C, vector that someone asked about? Oh, that's I said that's the center projection of the camera. Think of it as like the pupil. So where are you going to put that in your 3D world is related to this question. And then also related to that question is, what is the angular field of view that you're going to choose? That is, what angular, set of the scene are you going to choose to actually appear in the final pixels of your image? These are compositional questions at the end of the day about the scene and what you want to show in it. Good question. Do we use a standardized size of the focal plane, or do we just use the angle field of view? Great question. Great question. You're asking that question with a bit of geometric insight into what happens in a camera where you have a fixed size of the focal plane. I don't want to get into those details. That'll come in the camera lecture. For now, the flexibility in graphics of this kind is that you can just think in terms of angle of view. Okay, you don't have to think in terms of these millimeters I said before. Just know that's happening in real cameras. We'll talk about it later. But when you're composing things in your graphic system, you get to choose this angle sort of for free, okay, freely as you want. And another way to sort of think about it that's you'll see is like mathematically equivalent is that I could say, okay, I want this like angle of view here, 30 degrees, 10 degrees, 5 degrees. That'd be more and more telephoto, narrow field of view. Or I can actually just specify geometrically what the viewing volume I want is. We call this kind of a shape here in graphics a parallelepiped. This is the viewing parallelepiped. Okay, it's just like, a shape for this sort of, quasi, rectangular box that's sort of converging. So this blue thing over here. So we could just specify in terms of the coordinates in the world of these corners. Okay, so that's actually that's the common way it's done to specify what perspective view we want. So let me walk you through a little bit of detail about that now. The math in here gets a little bit more hairy. The equations are a little bit more ugly. I'm going to walk it through for you in a manner that lays it all out. And you can study it later if you want. But I'm going to focus on the high level bits, which is the connection through to the composition and the fact that the composition is related to this angular field of view, which can be related through to the key coordinates that we're going to talk about here. So to express this, you can talk in terms of like a near plane and a far plane. And then you could specify it in terms of the left comma bottom coordinates at the near plane, the right comma top coordinates at the near plane. Okay, does that make sense? And then where the far plane is also a common thing to specify. One thing I'll sort of observe here is that there's an aspect ratio that will inevitably get set when you define this. The aspect ratio has to do with the fact that, look, if you finally draw it to your screen has a certain width compared to its height, or the window that you're going to draw it into, depending on the size of your app, right? That you've resized the window of your app. It's going to have like a ratio between the width and the height. That ratio is something that you often want to match. You almost always want to match within the definition of this as well. Otherwise, you might sort of draw something that's kind of squashed horizontally or squashed vertically, depending on which way the aspect ratio is off. Okay, so that's sort of a minor trivial comment, but sort of an important one visually that comes up. Okay, so you can specify this perspective view that you want in this kind of a way, all right? So often what's done is to say, hey, I want a specific field of view in the Y direction, say this one here, FOVY, okay, in degrees, radians, as long as you understand what they are. And here's the width and height aspect ratio of my my frame buffer, and what the near plane I want to be and the far plane I want to be are. Okay, I mean, comment on the near plane and the far plane. The near plane and the far plane are just to say, hey, I don't want to draw anything that's closer than the near plane or anything that's further than the far plane. This is sort of a pretty common optimization in graphics because you typically have finite precision. So you just sort of say the things my whole world is sort of between. It's at least this far away from me, and it's no further than 100 meters or something like that. At least like 10 centimeters or 100 meters away. Okay, so that's what the near and the far refer to here. From these values, we can derive the top, bottom, right, and the left coordinates that I described over here. Okay, the left, bottom, right, top coordinates from these just by basic trigonometry. And then we can pipe those into a perspective matrix that's a 4x4 matrix, okay? Now, what's the perspective matrix that we want? We're like, what do we want it to do here? Okay, let's review a little bit. You've got an object in the world, your dinosaur, great, modeled in object coordinates. Then you put it into the world by saying, hey, I want the dinosaur to be this size and located here. Then I got a camera that's located over here pointing at the dinosaur, okay? The camera pointing at the dinosaur was the look at transform that we talked about last time that brings you into standard camera coordinates. And then after that, from standard camera coordinates, we want to project with a perspective projection, basically into the frame buffer with linear perspective. But in graphics, it's very common to go through an intermediate sort of a standard space here, which is called normalized device coordinates, NDC, which is basically kind of like something akin to a unit box. It's actually two units wide, but it goes from -1, -1, -1, -1, -1, to 1, 1, 1. And it projects this blue-shaped object with those converging blue rays. It projects it into a square like this. After this, we can just flatten it. We can project in Z, and then just take that 2D image and then scale it to the frame buffer width and height. Okay, so this will actually not be, things will look sort of squished in one way or the other in this normalized device coordinates before we go into the final frame buffer aspect ratio. And why do we do this exactly? Because it's easier to specify this perspective projection into normalized device coordinates, and then it's very easy to specify normalized device coordinates into like frame buffer units. Okay, because that just goes from here to 0, 0 to W, the width and the height. I'll show that final transformation from here to width and height in the very last slide of this lecture. Okay. Anyway, so this is the transform that we want to do, and a couple of notes that I put here. Number one, this need not be symmetric about the z-axis. That is, left bottom comma negative near here does not have to be the negative values of right and top. Okay, so left bottom doesn't have to be the negative of right and top, so it doesn't have to be centered along the optical axis, but we'll kind of assume that it is, just for simplicity here. Also, the transform that I'm about to show is a bit different than the simple one I derived up to this point in the lecture that takes all of the z values and projects it onto the image plane at D. The transform I'm going to show you is a little bit more complicated because it's going to try to preserve the ordering in depth. By ordering, I just mean if one object is at a smaller z versus a larger z in the real world from the view of the camera, the projective transform I'm about to show you is going to preserve that relative ordering. Okay, so the z projected value of the closer one is going to be smaller than the z projected of the further one. And here it is. What? Okay, so this is the perspective transform matrix. And it's got some weird stuff happening. Near over right, near over top, not so bad. I'm going to show you some examples of this. This stuff's okay. There's some weird stuff happening over here. It's the negative of far plus near over far minus near. And over in this value here is negative 2 times far times near over far minus near. What is going on here? This has to do with trying to preserve this depth ordering that I described above, on the previous slide. Okay. Let me just show you a couple of examples so we get a kind of an intuitive feel for what's going on here. Okay, so let's just take this point here, this coordinate at right, comma top, comma negative near. So it's this corner on the near plane of this projective frustum here, as we call it, or parallelepiped. Usually call it frustum. Okay, so right top, negative near, we multiply by this projective matrix. So what do we get? We can kind of crank it out. Okay, so the top one, we get near over right times right plus 0 and all the others, we'll get near out. So again, near over top times top plus 0 over else, so we'll get near out. And okay, so those are two. We can do the bottom column, 0, 0, negative 1 times 0 times all of these. We'll pick up negative near and bring it to near in the bottom column. That's good, by the way. Let's take a look at that. We got what we wanted in the sense that the top right corner in this frustum ended up in 1, 1, right? Because we'll normalize by this near value. So it'd be near divided by near, near divided by near in homogeneous coordinates. We'll get 1, 1 in the top right corner here, which is what we wanted. What about the negative 1z value? Yeah, you get the right thing. Near times far, it's kind of really ugly, fractions here, but if you crank it through, it turns out you get negative 1. Okay, so this stuff here is causing this projection of the frustum into this unit box, or this negative 1 to 1 standardized box in the z depth as well. That's all I kind of want to say about it, because the details, aside from the fact that it preserves z ordering and that it gets into this box, are not critical at all. Okay, and it works for an oblique frustum as I described, or you can version of this that works for an oblique frustum. And I'm going to go through a review of how the transformations come together, okay, which is right now. But before that, let me just take a quick gander here. Now, why does a near plane exist? doesn't it make sense to draw things that are close? Great question. Very natural question. The only reason that a near plane exists is because of real precision limits. Think of it as discretization in floating point, okay? That's a real and very serious issue that comes up in graphic systems. You could say, well, let's just use more precision, double precision, things like that. You could try that, but it can build up pretty quick. And in the history of graphics, it's been pretty expensive in order to consider that when building GPUs. So typically they've been floating point, 32-bit floating point, and there you don't have enough precision to just represent arbitrarily close to the camera all the way out to optical infinity. You end up, you'll see artifacts in your pictures related to discretization. So that's why this has existed in the spec usually. Is near assumed to be 1 here? No, near is not assumed to be 1 here. You can decide what you want it to be, okay? But it will get mapped to -1 in Z after that perspective projection I just showed. Okay, let me give you a visual recap of transforms. Okay, let me give you a list first, and I'll show you pictorially. So let's recap what we talked about. We have coordinate systems, for example, object coordinates for modeling like all the vertexes of like a mesh of the surface of a dinosaur. We can apply modeling transforms onto that to, like rotate the dinosaur around, scale it up to the size we want. We can have world coordinates and apply to place that dinosaur into the real world at a particular location and orientation that we want. When it's in the world, we can apply a viewing transform. This was the look at transform to get into camera coordinates. From there, we can apply a perspective transform that we just covered today and do the homogeneous division in order to get into normalized device coordinates that I just defined, NDC. After that, we apply a 2D screen transform to get us into screen coordinates, also known as the frame buffer coordinates that we talked about rasterization in. Okay, so that's a reminder of the list. Let's look at it visually. I'll use a different example from dinosaurs. I'll use CubeMan again here. So let's say we have like object coordinates for like a unit cube, okay? We can apply some modeling transforms and instancing of multiple of these cubes to scale them and rotate them and position them to get a rough outline of CubeMan. We can then apply a viewing transform for a camera that's say located up here, up and to the right in this cartoon, okay? And that will get us into camera coordinates and transform what? It transforms those cubes positioned in 3D space and orients them relative to the viewing direction of the camera up and to the right here so that you can see in this cartoon that you can kind of see it from the top right view. Okay, you can kind of see those cubes that way. Then what, perspective projection, what we just talked about today. We apply the perspective projection matrix that we just talked about today, and we need to choose, in this case, the frustum, the location of the top right and bottom left coordinates of the frustum in particular, okay? And also we talked about the near and far, primarily for discretization, floating point position reasons. But you do need the near plane in order to, figure out what that angle is from the top right and bottom left. Anyway, this is a drawing of the frustum here, and it projects CubeMan into normalized device coordinates, which run from -1, -1, -1 to 1, 1, 1. Okay, something that looks like this. Notice now CubeMan is no longer the right aspect ratio. He's sort of been stretched horizontally, if you can kind of see that. And the reason for that is that the last transform we're going to have is to project or just scale it actually in 2D from normalized device coordinates into screen coordinates from 0, 0 up to WH. And in this case, we happen to have like a frame buffer that was tall vertically. Okay, so it's less wide than it is tall in pixels. And this is the final set of coordinates from which we get back to the rasterization lecture. All of the quads here, the quadrilaterals here, which you can think of as like two triangles, okay, split into two triangles. Each of these and their vertexes, we want to convert into pixel samples, right? And the coordinates in which we'll do it are now in pixel screen coordinates. All right, or frame buffer screen coordinates. All right, so rasterization, and that's how we end up with final pixel values. Okay, so that's the recap of transforms. Some good questions. Why can't we project from screen coordinates, from camera coordinates to screen coordinates directly? We totally can. Okay, so you can think of it sort of as a way just to specify the pipeline And you got to, specify the mathematics for the perspective projection there. So that's been sort of abstracted mathematically that way. But to emphasize this whole sequence of transforms that we do here, each of these is a 4x4 matrix, okay? And I described last time that actually after you've described all of these 4x4 matrices and the order in which they're going to be applied to go from CubeMan original cube coordinates, cube vertex coordinates, through to their projected location in the screen, it's just going to be one 4x4 matrix that is a pre-multiplication of all of these matrices. And you just apply that one matrix to go directly from CubeMan object coordinates to screen coordinates. Good discussion. All right. As usual, we have there's a things to remember slide there. I'm going to leave it for the website. Okay. What I want to do now is move on to the next lecture for today and get started on this texture mapping. Let me reshare screen. Okay. Thanks for the questions. Thanks also, Rishi, for working in chat, and definitely raise up any questions if I missed any that you think would be helpful for me to cover. Okay, lecture 6, texture mapping. I've alluded to this already in class. We've looked at lots of renderings. They're not just like triangle meshes. There's clearly image detail that's going on them. And I mentioned them already. It's sort of like we take images and we paste them on. So as an example, on this ball here, which might be a triangular mesh of like a sphere, there's some kind of, mapping of this pattern, right? The red star on the yellow background onto this ball. On the floor here, this is almost certainly, in fact, I know for certain for this particular scene, it was not modeled as, tiny little darker and and less dark triangles on the floor. It's just too much detail. It's actually just a picture of wood that's been image projected onto the floor. Okay, so that's at a gist level what texture mapping, or at least 2D texture mapping, has been used for. Here's another sort of peek into it. You can use this in many layers in 2D graphics. So for example, in this scene, you see a bunch of pinballs. You notice they look a little scuffed up. This is actually the sequence of texturing that has been applied onto that pinball. So first texture that's just a flat color to give this red patterning at the neck of the pinball, and then put the Brunswick sign on it, put actually another little sort of decal of this logo of the brand of this pinwheel. You can see all the scuff marks that have been drawn here in sort of a darker color, almost like dirt. This one's a bit more subtle. Actually, something's happening here to texture map onto it, kind of like an indentation. It's like the details about this not just being dirt that's on there, but actually like as if it's been dented in, so that when we talk about sort of lighting functions next lecture, and shading approximations in real-time graphics for shading computations giving a lighting effect, the lighting effect is actually being applied here with texture mapping to give it more detail in there. And then there's a shine that's been applied to it, which is also a shading thing that we'll talk about next time. And it's actually also being applied with this texture mapping to guide the fine details of it to give it a more realistic appearance on these scuff marks. Yeah, this one here is something called diffuse lighting. And then this one over here is something we call specular lighting. You can think of it as matte appearance and sort of the shiny part of an object like this, those two aspects of its reflection appearance. Talk about all the details on that next time. So how does this work? Texture coordinate mappings. Thanks to my co-instructor from last year, Angju Kanazawa. Professor Kanazawa suggested to think of it like chocolate wrappers, okay? Here you have Santa Claus, and if you take it off the chocolate, then you can think of it as this kind of an object, okay? So this is kind of, it's like intuitively, it's like a shrink wrap, at least for this kind of object, onto the surface. You can, of course, map, things in a structured way as well. Think of it like a map from latitude and longitude onto like a sphere of the world. And here, let's talk about it a little bit, okay? So just to find a little bit of the math and these projections, there are 3 spaces that we can consider. The surface lives in 3D world space here. It's a, like a sphere in this case, right? Existing somewhere in 3D world. Every 3D surface position, like this one indicated here as an example, also appears in two other locations. It appears in a 2D location in screen space, as we've talked about. So think of it as the XY coordinates in the frame buffer, if you will. And it also exists in an image, or we'll call this texture space. So in texture pixel coordinates over here. So for example, that point there corresponds to this point near the east coast of the US in this drawing of the globe, okay? Which means that this point here is associated both with that frame buffer pixel location, but also with this underlying texture image pixel location over here. And so these are, it's at the end of the day, a mapping from texture space and the texture image onto screen space via a 3D model, okay, that this image is being addressed onto. Let's look at another example, okay? This can get pretty complicated pretty quickly. So let me back up for 1 second. You can see here how texture coordinates could come up analytically in very structured kind of ways. This is just a map of the world in latitude and longitude for, like the horizontal and vertical coordinates, which, by the way, as you can see by convention here, the coordinates will be U and V for texture space. For screen space, we'll go with X and Y, sometimes X sub S, Y sub S for screen. But typically XY over here in UV and texture space. Anyway, here's just latitude and longitude, which we know exactly where it would go onto a sphere from like polar coordinates. Okay, so very analytic. This one is clearly not analytic. Okay, can you see that? So there's a 3D shape of some kind of monster character's head here. Here's the reference texture image. If we zoom way in here, okay, this is the texture image. Actually, something weird has happened here that I'll comment on. You can see all the triangles drawn on here. This is not common for a texture image, okay? This is just for our visualization and discussion purposes here. Usually a texture image doesn't have these triangles. I'm just trying to draw it here so you can visualize in this picture here, which is the rendering of this 3D object with the texture applied. These are all the triangles in this 3D mesh. And you can see, for example, this orange triangle here corresponds to this orange triangle over here, okay? So we've taken this texture image and we've warped it and projected it onto this character 3D model here. And it's a complex mapping. For example, the artists here, in combination with the technical art and technical engineering module or tools used to create this, have done a couple interesting things that let's observe. The eye, because eyes are important for having lots of detail, I think, in the eye, I think we'd agree. And the lips also. You can see there's a lot of pixels, relatively speaking, allocated to the lips and the eye here. Okay, if you look in the zoom in, there's a lot of detail here that's represented in the pixels of this texture image. Whereas, for example, over here, this cheek is a really large surface area, but it kind of varies a little bit more slowly, maybe a little bit less important to have detail there. It's more smoothly varying compared to the eye. And you can see that the relative area in the texture image is less. This takes some kind of mapping point for point for every vertex here. What is the pixel location in this texture image and vice versa? It's taken some sort of decisions in this mapping in order to create these kind of sampling trade-offs that I just observed there. Second thing I want to just visualize for you is the texture coordinates themselves. So in this case, we're talking about 2D texturing, which goes from a 2D image onto a surface in 3D space. So here's a visualization that we'll use for texture coordinates for UV texture coordinates. Again, UV is just the horizontal and vertical location in texture space. Okay, that's all that UV is. And here I've just visualized it for you as a color, so you can kind of see where it's mapping on here. So we've mapped the U coordinate into like a red color. So RGB, the U goes into the R coordinate, and the V coordinate, the vertical coordinate, we've just put it into G. Okay. So for pure red, which would be U of 1, V of 0, that'll go to RGB of 100, which is red. Conversely, V maximum here goes to RGB of 010, so it's green. Okay, pure G. And if you didn't know this already, if you have all red and all G, all red and all green, but no blue. So RGB of 110, it turns out that color is yellow. Okay. If you haven't seen that before, you might want to go play with like a color picker. You can see that. We'll also talk a bit more about that in color, our lectures on color, which are later in the course. Anyway, so that's how to read this, okay? Green, red, yellow, and then every intermediate position mapping. You can read off if you had a texture map that had this coloration, then you could see on the object from its color what UV coordinates it mapped to in that image. Okay, does that make sense? But of course, if we swap this, red green gradient for a real image, such as this one that has detail in the eye, the mouth, the cheeks, and so on, then we get this drawing over here instead. But this is what the mapping of this particular coordinate, this texture mapping coordinate, what the coordinates look like. Let me show you another example, okay, of texture mapping coordinates. This is called the Sponza Palace, sort of a famous model in a certain phase in graphics for a lot of sort of research test cases. Anyway, in this model, here's what the texture coordinates look like. I'm just doing the same thing as before, this red, green, yellow gradient, okay? And just showing you what all the texture coordinates look like over every surface of this architectural mesh. What you observe is that it repeats. Okay, so on the ground plane over here, you can see that it's a repeating set of texture coordinates. It goes from 0, 0 up to 1, 1 in this square, and then it's repeated here. So it's the same, the texture coordinate here, this location is 0, 0 again. Up there it's 1, 1 again. That's what it means here, so on and so forth. And what's happening here, we're just tiling an image. That's all it is, okay? So in this architectural model, we're using these kind of stone textures, brickwork, stonework, or flat stone in order to map these texture coordinates and make them look like this. So if you look really carefully, you'll see that it's kind of a repeating pattern, okay, of those base images. That's another way you could apply texture coordinates. Let me just pause there and say, at that point, you're sort of like only bound by your creativity, and folks have only been bound by their creativity for authoring and modeling the application of image detail onto 3D models in order to create virtual worlds that have the kind of visual characteristics that you desire. And in fact, it doesn't just stop at 2D texture mapping, but has a whole bunch of different uses that I'll probably get to in the beginning of next lecture to show you advanced sort of texture mapping. But there are 3D texture mapping spaces, there are sort of lighting space texture mapping functions, and so on and so forth. For most of this lecture, I'm just going to focus on this 2D texture mapping model, but just know that you can be very creative here, and people have been, in order to get detailed data in images and other kinds of data that we'll talk about, or high frequency data onto your 3D models to create visual interest. But for the moment, staying with 2D texture mapping, let's talk about interpolation across triangles of these texture coordinates. Like, how's this stuff working in detail? Okay. And this goes by the keyword barycentric coordinates. Okay, barycentric coordinates is interpolation across triangles. Why do we want to interpolate or across triangles? Well, because we often may specify the values only at the vertexes of a mesh. We've talked a lot about how when you are modeling like a 3D object in the world, you can just specify its 3D mesh, right, as an approximation for its surface. So it's typical to talk at the XYZ location of those vertexes of those triangles in object coordinates. And you might also want to specify certain key object properties just at that coarse resolution, just at the vertices. And then we would think about interpolating them in between the vertices across the surfaces of these triangles continuously in rasterization. And that would give us smoothly varying values across the surface. So what kind of things might we want to interpolate? I showed you texture coordinates, okay? I showed you that red, green, yellow gradient. If we just want to specify those at the positions on the vertexes of that mesh, then in order to get a smooth gradient, we'll need to interpolate it within each of the triangles as well. We may also just want to interpolate the color, just specify the color at vertexes on the mesh, and then have it smoothly interpolate between them. We may want to specify the normal direction at each of those vertexes for various reasons. We'll talk about that more next time for sort of shading calculations. We might want to interpolate those smoothly. It'll look visually better. And then sort of creativity is your limit. What I want to talk about over the next few slides is how do we interpolate? Again, that's barycentric coordinates, okay? So here we go. Barycentric coordinates are just a coordinate system for triangles. We can use 3 coordinates for to specify a location inside a triangle called alpha, beta, gamma, okay, as you can kind of see here. And this location XY inside this triangle would have, sorry, let me back up for a second. If we specify some kind of value at the coordinates, I'm being abstract here, A, B, C. Those could be colors. Think about those colors for now. They could also be UV coordinates, okay, for A, B, and C. Anyway, if I want to know what is the interpolated value at XY, the barycentric coordinates alpha, beta, gamma corresponding to this location XY give us the formula for this. The interpolated value at XY will just be given by, very conveniently, alpha times A plus beta times B plus gamma times C. So this is a weighted sum of the value specified at the vertexes, okay? Now, right away, barycentric coordinates have unique, have a property that alpha plus beta plus gamma is going to be equal to 1 inside the triangle, okay? If all 3, always equal to alpha plus beta plus gamma, and you're inside the triangle if all 3 of these coordinates are non-negative, alpha, beta, gamma, all non-negative. I'll give you a couple of examples. If you're at A, so XY is located at A, then it turns out the barycentric coordinates, I'll show how we calculate these, in gory detail in just a few slides, but if you're at this location, alpha, beta, gamma is going to be 1, 0, 0, okay? So at XY, what is the interpolated value? It's going to be alpha times A plus beta times B plus gamma times C, which is just 1 times A plus 0 times the others is just going to be A, which is kind of what we want, right? We'd want, if you're at the A corner, or if you're at this corner, what's the value? We'd want it to be just the value that's been specified at that location. So we have that property. Similarly for B and C, okay, for B, at B, alpha, beta, gamma would be 0, 1, 0. At C, alpha, beta, gamma would be 0, 0, 1, okay? If you're at this point here, which is sort of the center of mass, it turns out alpha, beta, gamma is going to be 1/3, 1/3, 1/3. And it turns out that the interpolated value at that location is going to be 1/3 A plus 1/3 B plus 1/3 C. Okay, so a few examples. Yeah, great question. Thanks for asking it. Let me reiterate. So what is A here? What's B? What's C? I'm being totally abstract. Let me say it again. So A, B, C is anything that you can interpolate. Okay, I'll come back and be specific in a second. It could be a color. Okay, as long as you scale interpolate a color, weight it from 0 to 1. That's all that's required to sum up and add them together. That's all that's required to sum up 1/3 A plus 1/3 B plus 1/3 C here. It could be a vector, say UV of texture coordinates. It could be anything, okay, that you can weight by a scalar and then sum with other units of that kind. Okay, all right. Let's look at an example, okay, in color. Okay, so here A, B, and C are just colors. So VA, VB, VC in this case, is red here, green here, blue here, and this is a visualization of the interpolation across this triangle. You can see it's blue at that corner because we set that a color at that vertex to be blue and green and red here, and it interpolates between them. So you can observe it interpolates from blue through to red continuously, through purples here, from green through yellow. It's kind of a darkish yellow here, but from green to red through yellow, and yellow to from green to blue through blue-green here. Okay, so this is kind of an example of what it would look like for interpolation across here. How do we calculate these barycentric coordinates that I described up to this point and just gave you some examples for? Let's get into the math of calculating it. Okay, so now there's multiple ways to define the value of these barycentric coordinates that are all consistent with one another. I'm going to show you one here that uses proportional distances, and I'll show you another example later. They're not the only ways to define this. In this proportional distances definition, you can the point located at this location here has an alpha value that satisfies this relation in Euclidean distance ratio. In particular, if this is the point in question that has an barycentric coordinate of alpha for the first barycentric coordinate, then this distance here is alpha. It must satisfy that this distance here is alpha in ratio to this distance here being 1 minus alpha. And you have a similar construction for the other coordinates. So in particular, the perpendicular, and this is a perpendicular distance you might note, okay, compared to this line here, BC, the opposite line from A. So beta would be defined in the analogous way. You take the perpendicular line that goes from B through this point that intersects this other side. And this ratio here to this ratio here must follow the same rule for beta. And similarly for gamma, if you drop a line from C through the point in question to the opposite line, and those proportional distances must be the same for gamma. Okay. All right. So how do we calculate alpha exactly? Recall in lecture 2, we derived this line equation. We call it L of xy when we're given 2 points. In that case, it was P0 and P1 that I derived it for. Let's just call it PQ, okay, in this case. So let's just refresh our memory that the line equation LPQ for given 2 coordinates xy has a particular form. I just rewrote it here. But in particular, what it represented was it gave us a value that was proportional to the distance from line PQ. That is the distance of xy to the line PQ. LPQ was proportional to that. Okay, so LPQ of xy had this form. This is just copied from lecture 2 using xp, yp, xq, xq and yq, okay? And for the coordinates, obviously, of p and q. And we can use LPQ to define very compactly what alpha is, okay? Because alpha, again, will have to have, LPQ again is proportional to this distance here, okay, of xy to this line. We can take it back to this drawing that I had earlier. So if we consider this point here and we want to know this proportionality alpha to 1 minus alpha, we can consider both of those as distances from this line here, BC. So in particular, LBC, the line equation, given points BC for any given point xy. Think of those as the coordinates of this point in question here. LBC of xy is going to be proportional to alpha, okay? LBC of the point A over here, which has coordinates, well, xa, ya, is going to be proportional to this total distance from line BC to point A, which is what? It's proportional to alpha plus 1 minus alpha. So it's proportional to 1, okay? So the bottom is proportional to 1, the top is proportional to alpha, where the top is proportional to alpha. So that's why alpha equals exactly this quotient here. And we can just write it down. It's not a particularly, short thing to write down, but it just uses this line equation that we did from last time. So explicitly, alpha is equal to that quotient from the previous slide. There's an exactly analogous equation for beta that I've written down here. You could write down the exactly analogous equation for gamma too, okay? And it turns out if you did all the algebra, it would be exactly equal to 1 minus alpha minus beta. Not a bad algebraic exercise if you're wanting to really familiarize yourself with barycentric coordinates to just rederive this geometrically, write it down for gamma, just sort of crank it out and show that what I said before, alpha plus beta plus gamma is going to be equal to 1 for any point in barycentric coordinates is going to be true, okay? We're going to be tested on this in an exam. I must confess, I don't remember we've ever had a problem exactly related to this on an exam. Not that I recall, but it's possible. But I'll say that our exams are open book. Okay, so you won't be expected to memorize this or commit this to memory. But I think that understanding the derivation of where this comes from, which is very simple geometrically, is very much worth doing. Okay, and how we leverage this line equation from last time. I want to give you an alternate geometric viewpoint on these barycentric coordinates. Okay, I said it's proportional distances is one way to get to a definition of barycentric coordinates. I showed that to you. It turns out there's a proportional areas way to get this as well. So alpha, it turns out if you have these triangles that I drew here for any point x, y inside the triangle, if you break it up into 3 triangles and consider their relative areas a sub b, and a sub c, where a sub a is opposite the vertex A. Similarly for B opposite B and area A sub C opposite C. Then you have these ratios over here. So specifically alpha is equal to area A sub A over the full area of the triangle, A sub A plus A sub B plus A sub C. Similarly for beta and gamma. So there's one thing to take away. There's just a very natural, symmetry, very natural simplistic symmetry to barycentric coordinates. If you actually have to calculate them, the equations, have a little bit of math involved in them, but the geometric interpretation of them is intended to be extremely simple and intuitive. And so I encourage you to commit that geometric interpretation to memory. Okay, so that's barycentric interpolation. Okay, specify the value of something at the corner of triangles. Or if you have a triangle mesh, specify it at the vertexes of the mesh. And then when we're doing rasterization, we will interpolate those values across the triangle surfaces in order to interpolate those triangle mesh vertex values continuously across every pixel on that surface. Well, how would we find the 3 different areas? A good question. I didn't write it down there, and I don't want to. You can go look it up. There's something with cross products, that kind of thing. You can go calculate areas. I'm just in this slide just wanted to state that this is a fact. Okay, these ratios exist as well. But the way I showed the calculation of it went through proportional areas and the line equation. Of course, when you calculate it out from areas, you would hope that you end up with exactly the same equations and do well. Okay, but the math derivation in terms of areas is interestingly different if you want to go crank it up. Perspective, projection, and interpolation. Okay, so one other comment I want to make is that, if you have a texture here and you draw it onto a perspective quad, so you tilt that quad down, as you can see here in space, you don't end up with the right picture. As you can see, you end up with a picture, this is what you get, okay? And in particular, you can see it kind of has a kink here. It's a very clear visual kink. Can you see that? The correct image, if you actually took this in the real world and printed out this piece of paper and you tilted it down in the world and stared at it, it would look more like this. Okay, this is what we would expect visually. So there's a problem here. What went wrong? And what went wrong here is if we do texture mapping and we use barycentric coordinates interpolation as I specified it, it doesn't work for texture mapping coordinates with the perspective transform. We have to do one correction. I want to tell you, at least raise it to your awareness. What's happening in this image here is the simplest thing. We just specify the UV coordinates for each of the corners of these triangles. Actually, of this square rather. You can think of it as 2 triangles though. Okay, so specify the UV coordinates in texture space for each of these. And then we interpolate those UV coordinates using barycentric interpolation across each of the triangles. And then we look up those UV coordinates in the checkerboard image and we just draw that. Okay, so it's just using what I've described up to this point in class already. You'll get this. What went wrong? The net of it is that linear interpolation in the world, which is what's occurring over the surface of that tilted quadrilateral, yields nonlinear interpolation on the screen if you go through a perspective projection. Let me just show it to you graphically. I think this picture makes it sort of really clear what's happening. So by linear interpolation, I just mean linearly interpolating across this checkerboard here. I've just drawn it in cross section here, right? You can see that, okay, yeah, the checkerboard, even and odd rows still are all at equal intervals. Okay, it's linearly proceeding across. But when you project all of those through the pinhole camera model, because the parts of the rows of the checkerboard that are further away are going to project from a larger z, they're going to project after perspective division by z to a smaller distance here. Okay, so this height of this row here is linear. It's all the same in world in 3D space, but projected onto the image, it's smaller here than at the top, just because further stuff looks smaller after perspective division. So in order to get this correct over here, it turns out that you have to perform the linear interpolation in world coordinates rather than so you have to perform that linear interpolation of the texture coordinates after perspective interpolation. Okay, and this is done actually in GPUs in order to get this to look correct, to have all this look correct, so that you get this image instead of this image over here. I put up this slide when I left it in here on purpose. I was going to put up this slide because if we're in person, I just got a few questions on this on Piazza. I wanted to explain how this works. So I'll just take a moment to explain it now, but we don't have to do anything for today. I'll put this little bar up here. So for this week, everyone gets full participation points because we're doing this transition into in-person and working out our kinks. And then it turns out that because I've been unwell, we're virtual anyway. But anyway, this is the slide that we would have starting next week when we'll take this start doing this attendance thing. It's gonna be really simple. Let me tell you what will happen. If you're joining this from Zoom, do nothing. Just take a short break. Attendance credits automatic because it shows up in the Zoom system. 60 minutes of attendance, okay, to count for coming to lecture. If you're seated at Evans 10 physically, what will happen is that at some point I'll put up this slide in each lecture, and then you can just go to this URL, okay, tinyurl.com/184lecture. Keep it bookmarked. Just put your name, very simple, and maybe your SID. I forget what we asked. Very, very short. Click submit, and that's it. This is an attendance method that very lightweight that I got from John De Niro. The timestamp is what we'll use to figure out if you're there. So do it right when I put up the slide. Don't do it later, unless it won't count. You could just, you could just like text message your friends and be like, hey, now's the time, the slide is up. But don't do that, okay? Because we will audit at some point in the semester, and it's like not an audit that you'll be able to pass if you're not physically inside the room. And if you fail the audit, we don't want you to do that. There'll be some large negative consequence. And you don't have to do it, because all you need to do if you want to just watch lecture recordings afterwards, instead of coming to a live lecture, either Zoom or in person, totally fine. It's the policy on the website. Just come and add a comment onto the website on one of the slides. That's all you got to do. Okay. So you don't have to, and please don't, do the timestamp if you're not in class. Okay. So that's all it is. If you have any questions, in the interest of time, we'll handle it on Piazza. I'll keep going. Let me sort of tee up something that's going to happen, and then we'll continue the discussion of it on Thursday. Applying textures is sampling. I've already described exactly how we apply textures sort of geometrically, but now I want to sort of get into some of the mechanistic details. And I'm just going to observe at a high level, the main thing I think that's of intellectual interest here that's going to connect this part of the course through to sampling, anti-aliasing, and really deepen our study of that is the fact that applying textures is sampling. Let's take a look at exactly what happens. So here's a simple texture mapping operation in pseudocode. So how does this work? For each rasterized screen sample XY, what does that mean? We had a triangle, we rasterized it. Okay, we talked about that. We'll get a whole bunch of XY samples that are inside the triangle. For each one of those XY samples, we'll calculate its UV coordinates. We'll evaluate the texture coordinate values that correspond to that XY location using, for example, the barocentric math that I talked about, maybe the perspective division interpolation that I talked about, but basically think of it as barocentric interpolation. After that, we do a lookup. We get a color. Float 3 just means 3 values, okay? RGB, think of it. We get a text color by sampling a texture object at coordinates UV. All that means is I have some kind of texture object that represents an image, and I'm going to say, hey, give me the value of your image at the location in, and remember, UV are just continuous coordinates from 0 to 1. give me the value of your image at location UV. That's going to give me text color. Then on the screen at XY, sample XY, I'm going to set that sample XY's color to be texture color, the value that I picked out of the image texture. This is just saying in pseudocode the picture that I showed almost at the beginning of this texture lecture, okay? And the key I just want to observe is that, look, this is sampling because exactly in this step, we have a function. It's a 2D function, which is the image that's represented by this texture object. And we're going to sample it repeatedly at different UV positions. Those UV positions are going to come from screen sample XY positions, okay? But through the 3D geometry projection that we've talked about. And we'll get a whole bunch of these samples, and then we're going to draw them to the screen. And I will continue. That's the high level bit that I want to set. So as soon as I said this, one of the things I want you to be thinking is from signal processing that we've studied is sampling is here, which means that we probably are interested in aliasing artifacts. We should think about anti-aliasing. These are going to be huge core foundational issues that we'll have to deal with, okay, for texture mapping. We'll think about sampling rates, Nyquist rates, all of that stuff will come back, okay? And we'll think about it in the context of texture mapping. So that's what we're going to do and pick up from and do next time, okay? All right, folks. Good to see you all and have a good couple of days. I'll let you know whether we're going to be live on Thursday via Piazza.